All right, everybody, it's about 4 o'clock. I hope that you're all doing well. I hope you enjoyed that rain because now it's going to be like hot by the weekend again and sunny and all that. So we can't seem to get any consistency with that. But oh well. Before we get started on anything here, I just want to just make a quick note. There is a homework assignment number 6. Which was supposed to be due today, but you know something unprecedented happened. Something completely historic, which is I woke up this morning and I looked at my Canvas box and there was not one single person that had submitted homework 6 into the thing. Usually like a day or two early they start coming in. People are finishing up. Not one single person had turned it in. And I'm like, that must be telling me something. This must be a sign. And sure enough, I was talking to several people. I got your email. It sounds like just not because it's necessarily that hard, but it's just kind of long and tedious to do some of these recurrence relations. So let's just take an extra day on it. I actually have to be around quite a bit tomorrow because of I have a department meeting in the afternoon, and also my other class has a test next week. So I'm going to have some office hours, some extra office hours on Friday. From 6 to 9 p.m. And I'll actually probably be around in the morning as well whenever I get myself over here. So you could certainly ask me some more questions about it. You can also just come into Zoom. And of course I have hours tonight also. So after class tonight. So there've been a few people coming by and there's been a couple questions. So if you're feeling that way, like, yeah, I'm not feeling the greatest about this particular set. It's really just, from my perspective, I was reading my solutions. They are kind of long. My solutions are longer than a normal assignment. And I think it's just because of all the stuff you got to do with the induction, writing it all out. And, there's several problems like that. So let's take an extra day on that if you need to. Don't worry about it. And if you get to tomorrow night and you're still like, oh, I can't finish it, just send me an email. Let me know how you're doing with it. I'll do my best to try to. I'm trying to make this enjoyable and not stressful. So if that helps, I'm glad to do it. There will be another assignment coming next week. It'll be based on mostly on generating functions, which we're going to start today. However, it will also have some of this non-homogeneous recurrence relation stuff. Those problems are actually at the end of the next assignment. So if you feel like starting with the non-homogeneous recurrence relations, since that's kind of what we're talking about first, you might look towards the end of homework number 7 for some problems to begin with, and then you can go back to the generating functions ones later. I did not end up sending you a video, basically because none of the problems on this current homework are non-homogeneous. They're all homogeneous. So I decided that there was no need for me to make an extra video and make you spend extra time on that now. So that's kind of where we're at. It's just a couple of homework assignments this week. Does anybody have any questions? That's sort of the lay of the land here.
Thank you.
Oh, no worries. I'm always happy to help. We'll try my best. I try my best to accommodate here. Okay, so that's that. I did put on the board over here. Let me scroll this back around. I did put this recap up of kind of the general process for a non-homogeneous recurrence relation. The first thing you need to do is just ignore the non-homogeneous part and just solve the corresponding homogeneous recurrence relation. And for lack of a better notation, I'm just kind of superscripting this thing H sub n homog. And then we do have to find one particular solution to the actual given relation as it's presented. Okay, and we're going to practice that now on this example. And then the last step is to actually just add the two parts together. It's the same way it works for differential equations when you have a non-homogeneous differential equation. So you just add the two parts together. Now, there will be constants that have shown up in the process of getting steps 1 and 2 done, and you will solve for those constants only at the very, very end, right? So don't try to solve them ahead of time. You just have to wait until the very end to do that. Okay, so that's the 3-step process, and we just should probably practice it, I think, on an example or so. Is that okay? Everybody okay so far? All right, so I've got one up here, just so we could play around with it a little bit. And this one is kind of messy, actually, but I think my notes are gonna make it, come out nice enough. Here's my recurrence relation. You can see that it has order 2. And you can see that it's non-homogeneous because there are terms here that do not, this would be what I think I called this,
B of it.
B sub n, yeah, on Tuesday. So this is the non-homogeneous part. Here are your initial values. You notice you have 2 of them because after all, it is a second order recurrence relation. So the number of initial conditions should always match that. And so, yeah, we can take this in 3 steps to give the solution here. So let me start with the first step, which is going to be to just ignore the non-homogeneous part. So I'm just gonna write down what it would look like without the non-homogeneous part. And that would just be h sub n equals 6 times hn minus 1 minus 9 hn minus 2. Okay, and so as you remember, there was actually a 5-step process for solving these. The first of which was to guess q to the n as the form of your solution. So if you just take h sub n and you replace it with q to the n, and we just do that everywhere. So I'll go fairly quickly through this first step of these first few steps of the process. So you just replace the h's with the powers of q, and then you cancel as much as you can. In this case, you'll be able to cancel all the way down to q squared. And we'll have q squared equals 6q minus 9. And I think you'll remember on Tuesday, what I did next was I got everything onto one side of the equal sign. So in this case, that would actually be, I'm gonna go ahead and skip a step, guys. It's just q minus 3 quantity squared when you rearrange the equation. And so your roots here, which you have to have 2 of them, and you do, the roots are 3 and 3. Those are the roots of your equation. Okay, so I can now write down at least the form of the homogeneous part of the relation. So this is h sub n homog, right? And the way that's going to look would be, we have these powers of 3. Now this is repeated, right? So remember, we talked about this on Tuesday. If there's repeated terms, we have to stack n's in front of the terms. So I'm gonna have something like c1 times 3 to the n plus c2 times n times 3 to the n. Okay, and it's probably not a bad idea to put a little box around that because we don't want to lose track of it. We'll have to come back to this later after we get to the last step of the process. So this is just the first part of it, dealing with the homogeneous relation. Everybody so far so good? Okay, so let's move on to step 2. I guess I'm calling this 2 now, step 2. And this is where we are trying to figure out the particular solution. Now, I didn't write the full recap of this back on the board today, but let me just remind you that on Tuesday, I said that we're only going to be looking at non-homogeneous parts that are either polynomials or exponential functions. So in this case, I've chosen a polynomial, and then based on what that looks like, that dictates what the form of your particular solution is. If you remember what I said, I think on Tuesday, is if this was a polynomial of degree n, or of degree k, let's say, then this should be a general polynomial of the same degree, right? Does that sound right? So this is a quadratic. Okay, so then what I write down here should just be a generic form of a quadratic. I think I used d's for the coefficients last time. I'm not going to do that here. I'm actually going to use nicer letters like an squared plus bn plus c. I'm just going to write that. Yeah. Okay, so what we do is we literally just take this as a guess. And we plug it in everywhere that we have the h's into our relation. And we just try to see what that's going to give us. So I'm going to need a little bit more room. This is where it gets a little messy. Okay, it's not hard, like conceptually hard. It's just messy hard. So I'm going to plug this in on the left. So let's just plug this into the recurrence relation. So on the left side, I'll have an squared plus bn plus c. And the a, b, and c, these are to be determined. These are to be determined. And on the right side, I have 6, so this is equal to 6 times, let's just write down the n minus 1 version of this polynomial. So that would be a times n minus 1 squared plus b times n minus 1 plus c. And then we have minus 9 times the n minus 2 version of our polynomial. So I'm plugging into the original equation, right? Are we following this? Okay, so then here I'm gonna have a times n minus 2 squared plus b times the quantity n minus 2 plus c, like that. And then we still have the plus 4n squared minus 3. So all of that is also part of the recurrence relation. Okay? Now, the way to, this looks awful, right? But the way to organize it is get all the quadratic pieces together because they have to match up on both sides. And then get all of the constant terms that don't have n's in them, get those together, and they have to match up on both sides. So like terms have to match up is what I'm saying. So like if I look at the n squared terms, let's just see if we can get the idea of this. If I look at the n squared terms, on the left side, I obviously have just an a for the coefficient. So what we got here, guys, is a quadratic polynomial equal to a quadratic polynomial. So the coefficients are going to match up. So if I've got an a on the left, now I go over here and I figure out what are all of the coefficients of n squared. Well, here I have 6a with an n squared on it. Okay, and then here I have minus 9a, right? So minus 9a with an n squared on it, and then I have a plus 4. So that's what I've got so far. Okay, and actually, this is not so bad. If you just move all the a's to the other side, I believe you actually have 4a equal to 4.
Yeah.
So then a equals 1. So just like that, we already know what the correct value of a is. Does everybody follow that? This is just left-hand side and this is just right-hand side. You're just kind of, making a equality of the n squared coefficients. Now I'm going to have to do the same thing with the n term as well. So for the the n terms. So on the left side, on the n terms, I obviously have a b. And now I have to figure out the n terms on the right side, and I have to not mess it up. So there is a cross term here of negative 2n. When you FOIL out n minus 1 squared, you'd have a negative 2n, but you already have a 6a. So 6a times negative 2 is negative 12. Okay, and then right here there's an n that has a b with a 6 in front of it. So that's plus 6b. Okay, and then where's our next n going to come from? Over here, we're going to have minus 4n, but it's multiplied by negative 9a. So that's actually 36, I think, times a. And then here's a b and a 9 subtracted with the n there. So that would be minus 9b. And there is no n term on the non-homogeneous part. So that should be the whole thing. I don't like how this line looks. It's like a not equals to. Okay, of course I need to plug in a equals to 1 if I want to do that. So we could clean this up. If I plug in a equals 1, I'll have 36 minus 12, which is actually 24. And then 6b minus 9b is negative 3b. So if I just boil that down, unless I've screwed it up, I believe b should be 6. I think that's going to work for that. Okay, and then, so that's the n term. And then finally, we need to match up the constant terms. The constant terms. And for the constant term on the left, we have a c. And then on the right, let's see what the constant terms comes out to be. Here I have just an a. So this would be a 1 squared with an a and a 6. So there'd be a 6a. And then the constant term here, I have a minus 6b, right? And then plus 6c. That factor of 6 gets thrown into everything. Okay, what about on the next part? Here I have 2 squared, which is 4, but there's a 9a in front of that and a minus. That's going to be minus 36a. Okay, here I have 2b, right? But it's with a minus, and then there's also a negative 9a. So, sorry, it's just negative 9. So there's negative 2b and negative 9. That sounds like 18b, if I'm not messing it up. And then there's also a minus 9c. And we do have the minus 3 over here on the very end that has to be accounted for as well. So we get this kind of ugly looking expression, but we already know what a and b are, and it's not going to be that difficult to solve for c. So if I plug in 1 for a and I plug in 6 for b, I'll get 6 minus 36 plus 6c, and then minus 36 again, and then plus 18 times 6 is 108, I believe, and then minus 9c, and then minus 3, and I believe if I reorganize that, I'm literally doing this in my head right now. I believe you're going to get 4c on the left side, and if I take care of all of these constants, what's 111 minus 72? 39. Is that right? Yeah, I suppose that's right. 6c minus 9c, but 4c. That look okay? So c would be 39 over 4. I think I did that right. Unfortunately, it's not quite what I have in my notes. But that's okay. I think I might have messed up my notes. So this should be the c value, and that means that we can now write down our homogeneous part of our solution. It would be n squared plus 6n plus 39 over 4. Okay. So now we go to step 3, which is going to be the part I'm probably going to not fully do. Because I think the numbers are going to be too messy. Looking right? Okay, sweet. Yeah, so step 3 then is, I'm ready to write it here. I'm just going to write down the form of my final solution, C1 times 3 to the n plus C2 times n times 3 to the n plus n squared plus 6n plus 39 over 4. This would be the general form of my solution to my recurrence relation. And the only thing left to do now is to solve for C1 and C2, which you can use these initial values to do that. Okay, so the numbers are not going to come out good. If I plug in 0 for n, 41 is H0. So if I plug in 0 everywhere I see an n, I'll simply get C1 plus 39 over 4. Can I change my initial condition? Let's make it 41 over 4. Oh, I love it. Just don't do this on my exams. I'm just gonna change the problem. Yeah, let's make it 41 over 4. Because if I do that, now C1 is simply going to be 1/2. And that I can live with. So C1 is 1/2. So we figure out what C1 is. And now I'm going to find out, probably I don't like H1 either. But that's okay. We'll see if we can fix it to be something nice. Let's plug in n equals 1 into everything. So I'll plug in n equals 1 now into n, and I have 1 equals 55 equals H1. So everywhere I have an n in my formula, I'm now going to put a 1. So I'll get 3c1, well, that's actually 3 halves, plus 3c2 plus 1 plus 7 plus 39 over 4. That looks horrible. I'm
Six,
sorry. You know what?
six.
That should be 1 plus 6. Yeah, 1 plus 6. Thank you. Yeah, right here. This is a 6n. So I plug in 1 everywhere I see an n, and those are the values I'm coming up with. But what I'm going to do, guys, again, I'm going to change h1 to 55 over 4. So we're going back and changing the problem as we go. I hope it's okay with everybody. So now I'm gonna put this one over 4. And 55 minus 39, I think is just 16. 16 over 4 is 4. So I can basically say that 4 is equal to 3 halves plus 3c2 plus 7. If I'm not mistaken. And so -3 is equal to 3 halves plus 3c2. Subtract 3 halves from both sides, I'll get -9 halves equals 3c2. And so I'm just doing a little chicken scratch here, guys, but I believe, if I've done it correctly, that c2 is -3 halves. Okay, and if that is all good with everybody, then our final answer, I managed to salvage this one. Our final answer for hn would be, so let's plug everything in. 1/2 times 3 to the n plus -3 halves n 3 to the n plus n squared plus 6n plus 39 over 4. That should be our final answer. Seems okay, I hope. Looks good. So hopefully this makes sense, right? When you're solving for A, B, and C, you're setting the left-hand side equal to the right-hand side, and you just compare the different powers of n. And that creates the equations for you that allow you to solve for those constants. This one's pretty messy. I'm pretty sure the ones that I'll be asking you to do are going to be simpler than that. Is that a hint? Oh, no. Okay, good. Is there a question though? Anybody have a question on how that works? Okay, well, if you think of something later, it's fine. We can talk some more. The ones where the b sub n is an exponential function are much easier because you only have one constant. If you remember that it's just p times a to the n. So you're only solving for one unknown, and that's generally not going to be as messy as like what we had to do here. So this one was particularly brutal, but we managed to get through it. Okay, sweet. All right, I would like to change, I have 2 more things I want to do today. One is I want to do some group work, but before we do the group work, I want to just introduce this idea of generating functions to you. It's a really interesting approach to solving combinatorics problems. That's very algebra and calculus based. So we're going to get into a little bit of a different topic here. And this is going backwards in the book. That's why these problems occur earlier in the homework set, because we're going back to section 7.2 to talk about this. So I did 7.1 and then I jumped ahead. 7.4 was the homogeneous recurrence relations. 7.5 was the non-homogeneous recurrence relations. Now I'm going back to make up for what I skipped over, which is 7.2. And this is an interesting topic. I didn't used to do this in combinatorics, but it's really, an important thing to cover. I really wanted to figure out how to make time to include this. So let me tell you that basically we are going to make a one-to-one correspondence between sequences of numbers, such as this sequence right here. This is a sequence of numbers, H1, H2, H3, H4. We're going to make a correspondence between a sequence of numbers and a power series. an infinite power series, which is a very algebraic gadget. Let me write down a definition here, and then we'll obviously get into some examples as well. So let's assume we start with a sequence of numbers. So let's let H naught, H1, H2, and dot, dot, dot up to Hn. And actually, this can go on forever because, of course, n might be any positive integer. Let's let that be an infinite. I'm going to let this be an infinite sequence of numbers. Then its generating function. So there's a generating function that we will associate with this. So its generating function. Its generating function is the infinite series. It's going to be the infinite series. We're going to call this g of x. G for generating. And all it is, guys, is h naught plus h1 times x plus h2 times x squared. And dot, dot, dot. And then, of course, somewhere in the middle, there'll be hn, x to the n, and dot, dot, dot. This is an infinite series. Goes on forever. The coefficients of the series are literally just the numerical values that are in the sequence itself that you started with. So starting from a sequence, you can make a generating function. Exactly. Just as a quick little remark here, a lot of times you'll have sequences that are only finite. If your sequence is finite, then we can just basically terminate the series after a finite number of terms. So let's just write that down. If the sequence is finite, so let's just say h naught and then h1 and then dot, dot, dot up to, let's say, hk, and it just stops after, that many terms, then we can view it as an infinite sequence where you just have a bunch of zeros after this, right? So the rest of the terms would just not be written down. So in this case, we can still write down a generating function, and it would just be, instead of being a series, it would literally just be a polynomial. So h naught plus h1x plus h2x squared up to hk x to the k. So you would just have, that many terms. So it would just cut off right at that point. Okay. So let me write down a couple of examples here of generating functions, just to kind of get our feet wet. Let's do the generating function for the sequence. So I'm going to give you a sequence, and then we're going to write down the generating function. Okay, this will be pretty straightforward, I think. My sequence is going to be 1, followed by 10, followed by 45, followed by 120, followed by 210, followed by 252, followed by 210, followed by 120, followed by 45, followed by 10, and followed by 1. I better slow down. So that's going to be it, and it's a finite sequence. So I'm only going to have a polynomial for my generating function. It's just going to stop after the kth term. But what is it? It is, I might just call this g sub 10 of x, just to emphasize the role that 10 is playing in all of this. But it's obviously just going to be 1 plus 10x plus 45x squared plus 120x cubed, and so on. Maybe eventually I can just go with dot, dot, dot here, and we eventually get to 10x to the 9th, I believe. And then the last one is x to the 10th. I believe there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 11 numbers here. So the last power of x that you would see would be the 10th power. Okay, and I'm just curious, does anybody recognize those numbers?
Binomial coefficients.
Oh, Sergio's scared me. In the chat, did everybody hear that? These are actually the binomial coefficients. 10 choose 1 is 10. 10 choose 2 turns out to be 45. 10 choose 3 is 120, and so on. So this is actually expressible kind of in a nice way. We can write it as a summation if we want. Where, let's see, did I use a k for that? Yeah, I did. K is a index variable going from 0 to 10. Right, and then my coefficients are literally just 10 choose k, right, times x to the k. So you can check that out. When k is 0, we get just 1. And when k is 1, we get 10x. When k is 2, we get 45x squared, and so on. It goes all the way up. You notice that these numbers are kind of symmetrical around the 10 choose 5 is the one in the middle, right? All the others are just like so. And would there be any other way of writing this? Does that remind you of anything from a couple weeks ago? One more time? The binomial theorem, right? Remember the x plus y to the n is the summation, n choose k, x to the whatever, y to the whatever, right? Well, I see the n choose k, or it looks like the exponent would be 10. And at least one of my variables looks like it's had 1 plugged into it. This is literally, guys, this is literally just x plus 1 all to the 10th power, as it turns out. So you have a generating function that is a super simple expression at the end of the day. And it's for this is for a finite sequence in this case. Okay, so far the way this game is working, I'm giving you a sequence and you're writing down the generating function. Okay, but we're going to play this game the other way around as well. So, but for right now, I'm starting with the sequence and then I'm producing the generating function. Let's do one more of those over here. Again, we probably don't quite see why this is, such a great tool for combinatorics, but we're gonna get there. Just have to be a little patient as we develop this. Okay, so let's just do one more example, just to kind of keep this flowing a little bit. What about the generating function? The generating function for the sequence 1, 2, 3, 4, 5, 6, and ... forever. Okay. So what would this one be? Again, I can just write it down, sort of unsimplified to begin with. So the first term is a 1, and then the 2 goes with the x, right? And then the 3 goes with the x squared, and the 4 goes with the x cubed, and ... I'll just say ... It's just going to look something like that. And that's a perfectly fine answer. We could even probably write it as a summation again if we wanted to, but I'm not even interested in doing that right now. But I'm wondering, do these expressions look like anything you've seen in any of your math classes? Things like 3x squared or 4x cubed. Where does that come from? These are always like the first ones that I ask my students to do integrals of. So to integrate 4x cubed, because integrating 4x cubed would just give me x to the 4th, right? Sorry, I also forget my calculus. When I teach this class, I'm like, don't ask me to take any derivatives or integrals. It's like way too much. But actually, these are the expressions that you get when you take derivatives of just powers of x. So I am actually gonna write this down in a slide. This, by the way, this is a correct answer, but anytime you have an answer that has dot, dot, dot in it, is not considered a closed form. Right, this is a beautiful closed form over here. This is fully expressing the entire answer. Whenever you put dot, dot, dots in an answer, it's not called a closed form, and somebody could wonder, well, gee, I wonder if the pattern continues or not. There's always some doubt there. But what we can do is we can actually get a closed form for this, and I'm gonna show you how by using that trick I just mentioned. Each of these terms is the derivative of a power of x. So first of all, the derivative of 1 is 0. I'm gonna put a little derivative here. The derivative of 1 is 0, so I obviously can include that if I want to. The derivative of x is 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared, and so on, right? So it would look something like that. And now I have to ask, does anybody know, this is one of those, graduation. Did I talk about what I do at graduation?
Your binomial theorem.
No, we don't need that.
That's what I'm saying. That's what you sucked
Oh,
about.
is that what I said?
You said you asked
Oh,
about the binomial
I
theorem.
did talk about how there's a test at graduation, just to make sure there's no mistake. Well, this would be another one. Do we know how to rewrite 1 plus x squared plus x cubed? Have you seen that one? It's a geometric series, right? What does it translate into? 1 over 1 minus x. That's exactly right. So inside the brackets, right, I have 1 over 1 minus x, and that can be re-expressed in this manner. Now, that is actually not true for all values of x. Obviously, if x is bigger than 1, then the thing in here is blowing up to infinity, right? And if you put a number bigger than 1 in here, well, you'll just get some fraction. So what I should say is 1 over 1 minus x. It's just a side note, guys. It's 1 plus x squared plus x cubed and dot, dot, dot. But what I want to say is that it only converges. It converges when absolute x is less than 1. So if x is outside of that sort of interval from -1 to 1, then this will not actually work. Okay, but with this generating a function stuff, we're really not interested in issues of convergence. We're not going to be plugging numbers in for x, right? These x's are actually going to be placeholders for us as we solve problems. So it's actually not so critical that we worry about convergence issues, but I would want everybody to know that this is equal to that in the sort of algebraic manipulation that we're doing here. And now what you have is, well, this would also be a good question to ask everybody right before they pick up their diploma. Can you take the derivative of this quotient? So we have to remember the quotient rule, right? Does everybody remember the low d high minus high d low all over low squared? No, okay. They never taught it to me that way either. I had to try to memorize it. The derivative of a quotient, you take the denominator and square it on the bottom. And then to get the numerator, you have to remember low d high. So the bottom times the derivative of the top, which by the way is 0 here, minus the numerator times the derivative of the denominator. Well, the derivative of 1 minus x is actually -1. So you end up getting this expression right here, 1 over 1 minus x squared. So there's another, now you have a closed formula, not something with a bunch of dot, dot, dots on it. You actually have a closed form formula for this generating function, which is, a nice thing to be able to have. Okay. So far, so good. So given a sequence of numbers, we can try to write down its generating function. Now, there's no guarantee that you're going to have a nice clean formula for it. I've done 2 examples where it was very clean. But it turns out that if your sequence of numbers has a lot of good combinatorial flair to it, a lot of times those generating functions are very nice. They're very simple. So I'm going to press on here a little bit. But instead of giving you another sequence of numbers and then just generating the function from it again, this time I'm gonna kind of just go the other way around. I'm gonna try to start off with what would be a generating function and then just figure out what the coefficients would be. What sequence does it create? It's kind of interesting. So we're just reversing the perspective on it. Is everybody with me so far? Yeah, so far so good. Okay, great. So let's just do another example. But this time it's gonna be a little different. I'm not gonna start off with a sequence of numbers and ask you for the generating function. Instead, I am just going to, I don't know, I think I'm gonna take another derivative of this. I'm just gonna see what happens. So if I take 1/1 minus x and I decide to take 2 derivatives of it, let's just see what comes out of that. Okay, so what this would mean is that I am going to take the derivative. Well, I'm gonna take, so let's just write out 1 plus x squared plus x cubed plus dot. I'm gonna take 2 derivatives of that. Let's just write it out this way. So when I take the first derivative, I'll get 1 plus 2x plus 3x squared plus 4x cubed and dot, but I still have to take one more derivative of that. So I'm just putting my little prime derivative notation here. And let's write down the next term. The next derivative would be a 2 plus 6x plus 12x squared. I think the next term after that would be 20x cubed, and so on and so on. And so that's what it would be. So whatever 2 derivatives of this is, would be the generating function for these numbers. Okay, and we can take 2 derivatives of this pretty easily. So let's do it. The first derivative of it was already this much. So 1/1 minus x with 2 derivatives is already going to be 1/1 minus x squared with one more derivative to go. And let's use our quotient rule again, or you can use the power rule if you want to use a -2 exponent. You can do it either way, but I will just tell you, I'll let you check it for me if you want to, but it comes out to 2/1 minus x cubed. So on the one hand, when we take 2 derivatives of 1/1 minus x, we just use the quotient rule twice and we get 2/1 minus x quantity cubed. On the other hand, when we actually take the infinite series that represents 1/1 minus x and differentiate it twice, we get this right here. So these are equal, that means. That means that these are actually equal to each other. Because they were both derived from the same starting point, which is that I want to take 2 derivatives of 1/1 minus x. If we actually divide through by 2, we can actually get a nicer relation. So this is going to be 1/1 minus x cubed. And if I divide through by 2, I'll have a 1 and then a plus 3x and then 6x squared and then 10x cubed. And I think it's going to be 15x to the 4th. If you actually check it out, we can go dot like that. Those are going to be the terms. So what we have found is a generating function for the sequence 1, 3, 6, 10, 15, and so on. And I'm wondering if those numbers look familiar. The 1, 3, 6, 10. What was that?
Numbers.
The triangular numbers. Do you guys remember that basically the n choose 2? The n choose 2, right? So this is 2 choose 2. This is 3 choose 2. This is 4 choose 2. This is 5 choose 2. Isn't it amazing? Combinatorics shows up in the middle of doing calculus, right? We take 2 derivatives of this thing, and that's exactly what we get. So note that this is equal. I'm going to go ahead and just extend this, guys, so that we can see the whole thing here. This is 2 choose 2 plus 3 choose 2 times x plus 4 choose 2 times x squared plus, and so on, 5 choose 2 x cubed, dot, dot, dot. So thus, let's just make a quick summary here of what we've just observed, and then we may wait and come back to this next time. But the generating function for 2 choose 2, 3 choose 2, 4 choose 2, dot, 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 right? 5 choose 2, and so on, is simply 1 over 1 minus x quantity cubed. That's what it is. That's the generating function for it. That looks all right. Actually, if we go back to this one, if instead of 1 over 1 minus x cubed, we go back to 1 over 1 minus x squared, that was the generating function for this list. What is this list? Yeah, 1 choose 1, 2 choose 1, 3 choose 1, 4 choose 1, and so on, right? You know, there's a general result that is developing in front of our very eyes. That these binomial coefficients are showing up as the sequences that can make generating functions of the form 1 over 1 minus x to a power. Yeah, so in general, let's just see if we can write this down. In general, let me get my camera on this because I want to make sure that this gets into my video. You. In general, 1 over 1 minus x to the k power, right? It is going to be a series. Now I can't use a summation index of k right now because I'm using the k for this exponent. So I'm going to go back to n again for a minute. N going from 0 to infinity. And what the coefficient is here, guys, is the following. It is n plus k minus 1, choose k minus 1. And this is times x to the n. Let's check it out. When k is equal to 3, when k is equal to 3, then we get n plus 2, choose 2. Is that what we have here? N plus 2, choose 2. So 0 plus 2, choose 2. 1 plus 2, choose 2. 2 plus 2, choose 2. That's exactly this sequence, right? And in general, this is actually what it's going to end up being. Does everybody see that? So we could take more derivatives, obviously, and get these larger denominator powers. But in general, this is what it is. So you can derive it using calculus, using the ideas that I've just explained here, at least for k up through 3. Right? But you could do this for k equals 4 or 5 or 6 or so on and so forth. But there's actually a way to explain this a little differently as well. I'm wondering if anybody can think about that. Do you happen to notice this expression as being something that you ever saw anywhere before in this class? Stars and bars coefficient. Is this incredible? Did you guys think I was going to talk about stars and bars today? No. Probably not. Probably not. If I have n stars, right, and I have k minus 1 bars, then this was the number of ways of choosing n objects from k different types of objects with no constraints, right? Now, I would like you to maybe hopefully understand why the stars and bars is showing up here. If we think about this guy, right? So just take a quick note with me. I love this. I get so stoked when I see stuff like this happen. So this thing here is really 1 over 1 minus x, k different times, Would you agree with that? So it's 1 plus x squared plus x cubed plus dot dot dot, and then there's another 1 plus x squared plus x cubed plus dot 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 dot, and so on and so on and so on. There's k of these. K of these things floating around. Right? So you have k of those. And you know, if I imagined multiplying it out, imagine with me for a minute that I wanted to FOIL this out. So there's k factors of that. There's k factors. Now let's suppose I imagine in my head that I want to multiply this out. And I'm going to get all these different powers of x, right, as I FOIL it out. So the question would be, how many times does x to the n show up? Well, I'm going to grab some of these x's. I'm going to grab some of these x's. I'm going to grab some of these x's. I grab some x's from each piece, right? And in total, if I want to have x to the n, the total number of x's that I have to grab is n. So let's imagine taking e sub I x's from the ith factor of this, you know, or the ith, let's say the ith copy of 1 plus x squared plus x cubed and dot dot dot. Well then, how can I end up with a total of x to the n? Like, how many ways would there be to do that? Well, I would grab e1 x's from the first pile. In other words, I'd grab maybe 3 of them, right? I'd grab one of these terms. Then from this term, I'd grab some x's here. So that would be e2. And then I keep going and going. I have a total of k of those to choose, right? So I pick some x's here, I pick some x's here, I pick some x's here. I don't know how many I'm going to pick, but in total, I better pick n of them to get x to the n to show up. And so how many ways are there to make an x to the n term in my power series expression here? Well, that's whatever this coefficient is going to be. And what is it? Well, it's the number of solutions to this equation using non-negative whole numbers for the e's. That is a stars and bars problem. You have n stars and you have k minus 1 bars. It is exactly this many ways. Such an interesting development. You would never have thought that somehow playing with these generating functions, these infinite series, was going to somehow have anything to do with stars and bars, but it actually does. So you can prove this formula either the calculus way that I was explaining here earlier by taking derivatives of 1 over 1 minus x, or we now have a completely different way of understanding the same formula, which is that it comes from solutions to a standard problem on stars and bars. Okay, so you could actually prove this without ever using calculus after all. You still have to know the geometric series, but you could make all of that headway without ever using calculus at all. Oh, wow, I love it. I just love that. Okay. Yeah, I think I pretty much explained all that stuff in my notes. Let's suppose that you are sent to the store to grab an odd number of apples. So I know earlier we did this grocery store thing where there was an infinite number of apples and oranges and bananas, and I would say things like, oh, you should take at least 3 bananas and at most 4 oranges, and we did, you know, subtraction tricks and all this kind of stuff to solve it. But what if it was something about taking an odd number of apples? So you can take 1 or 3 or 5, or maybe the number of bananas has to be a multiple of 5, something like that. You might wonder if you would be able to count how many solutions there were to that kind of problem. And it turns out that we can use these generating functions to do it by just putting only those exponents here that we want to allow. So this could be the bananas term, and this could be the oranges term. And then you can just say, oh, well, if you're only allowed to take an odd number of bananas, then I'm only going to have the odd powers of x in the series. And you can actually then figure out, well, what would be the coefficient of, let's say you want 18 pieces of fruit. What would be the coefficient of x to the 18 under that scenario? So I know I'm not writing any of this down now. I will next time when we actually show how that can be done using generating functions. I think I'm gonna tease you with that though until, what is today? Today's Thursday. Today's Thursday. So until Tuesday, I'm gonna tease you for 5 days because I want to give you some time. I have a group work here that I'd like to give you some time to work on. It's kind of a long one actually, so you probably won't even finish it, even if I give you 20 something odd minutes, but see what you can do with your groups on these problems. There's some nice ones here. And I'm gonna come around as I always do and try to poke you in the right direction with these problems. And you should just be pretty familiar for occurrence relation stuff. And we just need. And I will erase the board and let you guys have at it.